Oh, cool. I can walk around. I like to walk. Is that working? Just getting mic'd up. Okay. I've studied a variety of terrestrial and astrophysical sources over the years, and today I'm going to be sharing with you one of those sources that I've been studying more recently, both experimentally and theoretically. And it begins with the production of hydrogen cyanide in early Earth's atmosphere and follows through rainout to so that hydrogen cyanide can react in warm little ponds to produce the building blocks of life. And I focus on the building blocks of the information polymer that's thought to make up first life, which is RNA. And a lot of this stuff David Catlin and Paul Rimmer introduced, so that will also save me some time. I want to briefly acknowledge my collaborators first. Can I? Okay. Dr. Sarah Hurst and Dr. Chow He. That's the PI of the lab that I work in and the scientist who built the experimental setup that I've been using over the last year, which I'll be sharing with you today. Dr. Ralph Pedritz, Dr. Karan Miller-Verdicani, and Dr. Thomas Henning have been involved in the atmospheric modeling that I'm going to be sharing with you, which is based on hydrogen cyanide production in early Earth's atmosphere. So, let's begin by imagining a warm little pond on early Earth. And as has been previously mentioned, these are excellent environments for the polymerization of RNA, as they have periodic wet and dry cycles on the order of seasons, days, and sometimes even hours. So I asked the question, if life emerged in this environment, how did it obtain its building blocks of RNA? Well, there's a few options. Meteorites have been known to carry a vast inventory of biomolecules, including nucleobases, ribose, amino acids, fatty acids, and certainly these things can leach out of the pores of a meteorite that lands within this pond. Dust, interplanetary dust, can also be a potential source. Although interplanetary dust hasn't been detected to have biomolecules in it directly, there have been many lab experiments which have produced biomolecules on analogs to dust by irradiating them with UV light. And it seems pretty easy to make nucleobases, ribose, amino acids, fatty acids on dust. But if you didn't need external delivery, if Earth could have made biomolecules on its own, well then whatever rained in the pond is going to make up your pond solution, and this is going to be what you're going to have to make your biomolecules out of. And this is where hydrogen cyanide comes into the story, as it is a key precursor to a variety of biomolecules, including nucleobases and amino acids. And there's been several models, 1D photochemical models, which have shown hydrogen cyanide production in early Earth's atmosphere, including two of the scientists that are here and just spoke before me, Paul Rimmer and David Catlin. So I'm going to be sharing with you some of my models as well. And I'll just mention another piece of work done by another scientist in the audience, Dr. Zoe Todd, which is kind of a hybrid of an exogenous delivery and an in situ production, where instead of delivering the biomolecules by meteorites, you deliver the precursor to biomolecules by comets. So this is similar to in situ, but also has an astrophysical component. Okay, so the research that I'm doing is grounded in the Miller-Urey experiment, and this has already been introduced, and everyone knows this pretty well, so I'll be brief. Here's the apparatus that Miller used. Put some reduced gases into this apparatus and exposed it to a spark discharge to produce hydrogen cyanide. That hydrogen cyanide then condensed out into this warm little pond below, right here, and we found several amino acids in that original experiment. Now there's two interesting things about this experiment that I want to mention. The first is that if you put in oxidized gases, it doesn't produce as much hydrogen cyanide, and therefore also doesn't produce as many biomolecules. And you can see on the here as you go from 17% CO2 to 50% CO2 in this experiment, you drop by 3 orders of magnitude in your hydrogen cyanide yield. So that's pretty substantial. The second thing that's interesting is that there seems to be a constant relation between the methane content and your hydrogen cyanide yield. In other words, there's a linear relation between your methane abundance and the amount of hydrogen cyanide that you produce in this Miller-Urey experiment. So you can imagine the more methane you have, if the yield's staying constant, the more hydrogen cyanide you can ultimately get, and therefore the more biomolecules you can produce within your pond in a more concentrated solution. So let's get to the experiments that I've performed. Here is the phaser experimental setup. You can see a chamber here, which has 2 electrodes. We apply voltage difference between them, and we get cold plasma discharge. This is an ionization of the gas between the 2 electrodes. And this is essentially electrons, which are bombarding the gases to dissociate them, to produce things like hydrogen cyanide. Now, this we use as a laboratory analog to shortwave UV production, similar to what's occurring in the upper atmosphere. This is a vacuum flow system, so these are very low pressures. We're simulating up in the upper stratosphere or the mesosphere. And we do have a UV lamp in the lab, but there's a reason why we don't use the UV lamp in these experiments. Does anyone want to guess?
You don't have the proper sunglasses?
No. The reason is that UV lamps, they don't go low enough in energy or low enough in wavelength to dissociate the N2 bond. And we have N2 in our experiments because we're doing Hadean Earth. This is the main source of nitrogen atoms. So we need to be able to dissociate N2. So we need wavelengths lower than about 110 nanometers, whereas UV lamps only go down to about 110, 120 or so. So we use electrons instead as a laboratory analog. You can also see we have connected an RGA mass spectrometer. This is how we detect our products. Here's a schematic of that setup. We put in any gas mixture we like. In our case, we're doing Hadean Earth experiments, so we put in mostly hydrogen, and David Cavan motivated why we can have a hydrogen-dominant atmosphere. We also put in methane and nitrogen. This flows through our vacuum flow system. We can introduce water, or vapor, using a dry ice bath. This flows into our chamber here, where we expose it to the cold plasma discharge. And then our products flow out. Most goes out the pumps, but some of it goes to our mass spectrometer, where we can measure how much hydrogen cyanide we're producing. Here are some of those plots. Well, that doesn't turn out really well, but you can see from our 5 experiments, which go from 0.1% methane to 0.5 to 1.5 to 3.6 to 6.5% methane. We have a peak here, which is the 26 peak, and you see it decreasing as we go to lower methane to an amount that's just a tiny shoulder, any lower than 0.1% methane, and we're not going to be able to see any changes in our spectra. Now, this is the key thing. This is a 26 peak. Typically, you'd like to detect HCN in the 27 peak, rather than the cyanide fragment, the hydrogen cyanide fragment. But this is washed out in all of our spectra because of the dominant 28 peak you see here for N2. This was a problem because we want to be certain we're detecting HCN, and the 26 peak can not only be due to cyanide, but also to hydrocarbons, which are almost definitely being produced in these experiments as well. So if all I had to work with was experiments, I would have to stop here and say, well, maybe we made hydrogen cyanide. But I come from a theoretical background, and I have a few more tools in my toolbox. So I decided to go to plasma modeling to figure out what the most likely source of this peak was. So we did 0D plasma modeling. We used 3 different chemical networks just to make sure that this wasn't network dependent. Krakenow, which is the one I developed during my PhD, which is experimental rate coefficients when they're available. Otherwise, we calculate them using quantum chemistry, using consistent methods. And there's about 100 reactions that we discovered in this network for the first time, which was a lot of fun. We also use the Herbride network, which is used for HCN production in Titan's atmosphere, and the Venois 15 network, which has 2,000 reactions. Just wanted to get a big one in there as well. We also use 2 electron energy distribution functions, basically how the electron energies are within our plasma chamber. Maxwellian is if you have thermodynamic equilibrium between your electrons and your plasma, which is probably not the case. We're probably more in the Joy-Weston regime. But we modeled all 6 of these scenarios just because we wanted to be as thorough as possible. And you can see at 1 second, which is how long the gas is in contact with the plasma, this black line here is hydrogen cyanide, and it's the dominant product in all of our plasma models. So looking at this, we conclude that about 60 to 100% of the 26 peak is due to hydrogen cyanide, with 0 to 40% being from C2H4 and C2H2. So there is probably some contribution due to hydrocarbons, but the dominant product is HCN. So this was great because this really shows the power of combining experiment and theory. You know, we get to learn more with both of these than we could ever learn with just one of them on our own, on its own. Here we can see the theoretical models on the left for the 5 different experiments. So we get an increase in HCN from an increase in the methane, and that's plotted in the black dotted line here. The 26 over 28 peak increase from our experiments are plotted. All of the experiments are in red here, and the line of best fits in green. And you can see we have 2 lines which overlap quite well, and you know, in science, this is the thing that we really cheer for. We like it when our theory and our experiment match up. This tells us that our theory is likely doing a good job at modeling our experimental setup. The slope of this line is 0.13, HCN to CH4. This is a 13% yield. And excitingly, this happens to be right in the area of the Miller-Urey experiment, which is a completely different simulation in a glass apparatus with lightning discharge rather than analog to UV radiation. But they got within about 9 to 14% yields. For higher abundances of methane than we use, 17 to 50, we used 0.1 to 6.5. So it seems like this relation of about 13% yields kind of extends, you know, from 0.1 possibly all the way up to 50% methane. And the great other thing about doing theory and experiment together is you can learn exactly how hydrogen cyanide is produced. So we ran a sensitivity analysis by removing one reaction at a time and found out how HCN is produced in our experiments. And this is the method. This is the mechanism. Nitrogen attaches to a CH3, pops off a hydrogen, and then a single hydrogen atom will steal another hydrogen from H2CN. And these are actual quantum chemistry simulations here, where it's showing the transition state between all of these reactions. Okay. Now this is 0 dimensions, and that's very different than a planetary atmosphere, which is in 3 dimensions, but we're going to increase by 1 dimension and just do 1-dimensional chemical kinetics instead. So slightly better than 0 dimensions, but now we can encapsulate all the physics that's occurring in the atmosphere and figure out how does methane relate to hydrogen cyanide production in a more complex environment. So we ran chemical kinetic models using the Krakenow network again. We used an atmospheric chemistry code developed at the Max Planck Institute for Astronomy, and we calculated our pressure temperature profiles using a radio transfer code also developed at the Max Planck Institute for Astronomy called Petit-Radtrans. We modeled 2 epochs at 4.4 and 4.0 billion years ago. So in the Hadean, when we expect life to have emerged, these represent a hydrogen dominant and CO2 dominant phase, and they vary in the bombardment rate, the luminosity, UV intensity, and lightning chemistry. We then couple hydrogen cyanide rainout from these models to biomolecule production in our pond models that we developed in 2017 for different purposes, for comparing meteorite and IDP, or dust delivery of nucleobases. Here's a schematic of those models, broken down to the sources and sinks of 4 key molecules, hydrogen and CO2, determine whether you're reducing or oxidizing. Methane, as we know from experiments, is the main precursor to HCN. So breaking this down, our main source of hydrogen is impact degassing, which David Catlin introduced. This varies depending on the bombardment rate. Yeah. So at 4.4, we had a higher bombardment than at 4.0. So the amount of hydrogen entering into the atmosphere is going to be higher and allow for this reducing composition early on. CO2 is coming out of volcanoes in all of our models. We know from zircon analyses that the mantle was relatively oxidized as early as 4.4 billion years ago, so we're not really going to get any H2 coming out of volcanoes. So these two are battling each other, and eventually there's a transition from reducing to oxidizing due to these two battles that are occurring and the escape of H2 to space. We model methane coming from hydrothermal systems. This is not a very efficient way to make methane. Can lead up to maybe 1 or 2 parts per million in the atmosphere. This is where you have serpentinization of ultramafic rocks at the seafloor, reacting with CO2 to reduce it. And then hydrogen cyanides produced from the lightning and UV dissociation of methane and nitrogen, these radicals reacting with that reaction that I showed you in the quantum chemistry simulations a slide ago. Here are our results. So we have 4 different models, reducing on the left at 4.4 and oxidizing on the right. We have both formaldehyde in solid lines and HCN in dotted lines because we wanted to know whether formaldehyde could have come from the atmosphere, and it turns out in our models it's not very efficiently produced in either reducing or oxidizing conditions. 10 to the minus 18 and 10 to the minus 14 or 13. So fairly negligible, likely did not come from the atmosphere. That's okay, you can still get it in a pond from aqueous chemistry. But hydrogen cyanide was formed in our reducing model at about just sub-part per billion. In our oxidizing model, not so much. So in 1D, we also see that there is less hydrogen cyanide produced in the atmosphere in oxidizing as in reducing conditions, which agrees with the Miller-Urey experiment. So that didn't necessarily have to be the case. This is more complex than a Miller-Urey experiment. It's a 1D atmosphere rather than 0D experiment, but we see agreement there. Here's just the surface of the surface layer of our atmosphere, and I just want to point out methane in pink and HCN in purple. You know, we saw a linear relation in our experiments in 0D, so now this is asking how does this relation look in 1 dimension at the surface, and we see that it's not perfect. They don't line up in time perfectly, but you can see generally if you have more methane, you get more HCN. Then on the right, when you have less methane, you get less HCN, and they follow each other somewhat. So we didn't expect it to line up perfectly, but it lines up somewhat there. We want to know whether UV or lightning was the main production mechanism for HCN, or the main energy source. So we turned off photochemistry on the left and turned off lightning on the right. Without photochemistry, we don't really make very much HCN. So this is not your classic Miller-Urey experiment where it's simulating lightning. This is not a very efficient way to make HCN because lightning is dispersed over the surface. Although it can produce a little bit locally, it's going to quickly disperse in the atmosphere. So it's mostly coming from UV photochemistry, which makes a lot of sense because a whole hemisphere of the Earth is irradiated by UV light, whereas lightning is more locally occurring on the surface. All right, and I'll just finish with, or I just have a couple more slides. This is kind of the finishing of this story. We rained out hydrogen cyanide in these models and produced biomolecules using experimental yields, and we see for our oxidizing model, we don't get very much nucleobases. This is 10 to the minus 6 micromolar, so picomolar, I guess. Reducing model gets up to the nanomolar, which is also very low. So we turned off seepage in our reducing model to see if this could maybe provide us a little boost. You can imagine this as the David Deamer, Bruce Damer scenario where you have, amphiphilic multilamellar matrices clogging up the pores at the base of your pond. This could potentially allow a little higher concentration. And we get almost up to the micromolar for some of the nucleobases. the biggest increase to uracil and thymine because their hydrolysis rates are lower than the other nucleobases, so that's the next most efficient sink. And we also have stuff like 2-amino-oxazole in here and ribose, as we are agnostic as to how you make nucleotides. Okay, so when did life emerge? Because we see this big difference between the reducing and oxidizing phases. This really points to around 4.5 to 4.3 billion years ago. This is very early, but this is when the reducing atmosphere was present and produced more hydrogen cyanide. And I'll just finish on this last slide. I have one more source to test, and this is what I'm working on right now. We also produce organic hazes in these experiments. You can see here some kind of chocolatey-like solid particles on the bottom, and it also is on the sides, and I scraped it off, and I got about 500 milligrams in this experiment. I took this to the University of Northern Iowa, and I put it through triple quadrupole GCMS, and these things have nucleobases and amino acids. So the next question I have is, how does that compare to HCN production of biomolecules? Could organic hazes be the more abundant source of biomolecules to wormhole bonds? And I'll put in my key takeaways. Thank you very much.
Thank you. Thank you. Questions? Rich, thank you, Ben, for a really, really nice talk. I was kind of curious about one of the things that you were talking about using these electron sources because you need the shorter wavelength light instead of UV lamps. This would seem to also be consistent with the way that you would move through a particular atmosphere, and I guess this also fits with your models, where you break your N2 apart in one place, and then you break your methane probably in a different place. Is there a way to try to experimentally capture that? And is there any point in doing that, or do the models do well enough anyway that really all you're looking at is mechanism at that point?
I suppose you could imagine an experiment where you have them occurring in different places, but I guess it doesn't really matter to us as long as you can dissociate N2 and methane, and there's some sort of turbulent mixing in your atmosphere, and these things can come together somewhere. We're not trying in these experiments. We're not an exact simulation of an atmosphere anyway, because it's essentially a small, tiny chamber. It'd be great to have a cool, 10-kilometer sized apparatus where you could get some mixing occurring and different zones of dissociation. That would be amazing. And maybe something we should work on, right? Think about. Apply for a grant. As far as this goes, we proof of concept in the experiment, and then the atmospheric models tell the rest of the story.
In that case, just a quick follow-up question. The yield that you got from the experiment, is that consistent with what you get from your photochemical modeling with the environment that you have there?
Yes, yeah. So in the upper atmosphere, in our photochemical models, we see somewhere between, I think, 20 and 40% yields. So we got 13 in our experiment. Within error bars, it's fairly similar. Yeah, thanks. Yeah.
Neat to see your work, Ben. Thank you. In your final slide, where you have these precipitates in which you can find nucleobases, I'm curious how much diversity there is in the actual material, how much you know about its content, and how much you can attach a process model. And I'm asking the question from a particular angle. In biochemistry, adjacent to the purine nucleosides, not only to nucleobases, but to a more complicated thing, you have whole clusters of cofactors that are rather diverse. They're electron transporters, root transporters. We tend to inherit a history that's very focused on RNA, which takes on its meaning when it is concentrated, purified, oligomerized, and regioselected, and base paired. But of course, the point about the cofactors is that whatever meaning they have is carried in the organic chemistry. And I'm always curious in these experiments how much complexity there is and how much, if we know about what's in it, in what cases there may be functional consequence that's carried at the level of small local organic chemistry and not waiting for sort of further accretion to bring it out.
Yeah, great question. So there, in the analysis that I've done on these hazes, there is a bias introduced because with triple quadruple GCMS, you will only find what you're looking for. So in that sense, I've developed the protocols to detect nucleobases, not even all of them, just seven of many, as well as amino acids, and then a few other organics like urea and stuff like this. And I found all these things, which was very surprising. I mean, I expected, I didn't find every amino acid that I made a protocol for, but because of the diversity in the percentage of things that I found that I was trying to look for, I would say that there's probably a ton more diversity that hasn't been uncovered yet. And I would like to develop protocols to try and cover a lot more. In that sense, I also would like to remove my bias and find out what other people would like me to look for, so that I could, look for everyone's favorite biomolecule precursor. Because, I don't have any preference over what the route to nucleotides is, for instance, or what's involved in different metabolic pathways that could have been important for producing the genetic code and things like this. So yeah, I'd love to hear your thoughts on what else I should look for.
I just want to point something. It's a really great question, and thank you for asking it. And I really like to think about the environment as being dirty water, and it's producing all kinds of things, and that's kind of the challenge we have to characterize them all. So, of course, you have to start cleaner to see what happens and then go to the dirty conditions, but that could actually make it a lot more optimistic than your takeaways, for example. You don't have to do everything during the first 200 million years. If you store some of this CN in the lake, you can use it over a much longer period of time for your chemistry. So I think this is really a great way to think about this. Yes?
Yeah, Janina Hansen from ETH Zurich. So this will be a very naive question. What makes hydrogen cyanide such a favorable foodstuff for periodic chemistry, and are there other possible foodstuffs?
Yeah, so I have one answer that I wrote down in a paper once when a referee asked me why, which is that our HCN likes to polymerize. It likes to react with itself and other small molecules. It does this really easily in liquid, in aqueous solution. And it is also abundantly produced in photochemical models. So this transition from gas state to aqueous state, where it's stable in gas state but less stable in aqueous state, kind of makes it a perfect molecule to put from one environment into another to create prebiotic chemistry. And then the other potential sources, Zoe Todd can talk about cometary, possibly delivery of HCN. That's a potential external source. But as far as terrestrial sources, it seems like photochemistry is the main one.
Thank you.
Yeah.
Well, that was an excellent talk, and all the talks this morning, so let's thank the speakers. And we have coffee break now for 20 minutes, so back here